Hi, welcome back to my YouTube channel. In today's video, we're going to look at the turning point, the maximum and minimum values of functions. So let's just get right into it. So in this particular problem, there are two ways we are going to solve this particular problem. So whichever one looks very comfortable for you, you could decide to use that in your problem solving and in your exams. So let's just take a look at the two different methods of solving this problem. Okay, so so the first thing is, if you want to find the turning point, so another way to say turning points is basically stationary points. So sometimes they are called stationary points, and sometimes they are called critical points, right? So when they use these languages, you should understand that they're talking about the points where we have minimum values and maximum values and sometimes saddle points of the function. Okay, so let's just take a look at this. So for us to find the minimum or maximum value of this function, the first step, so there are several steps that you need to follow. Okay, so the first step is to take the derivative of these functions to find the critical point. Okay, so the first thing is to find the critical points, and then we classify these critical points later on. So to find the critical point, what you need to do is to find the derivative of the main function with respect to x. Okay, and we equate this derivative to what? 0. Because if they are, think about it, if they are turning points, we expect the derivative to be 0 at those points. So let's say you have a function this nature. So let's say you just have a function. Now think about it. At this point, the derivatives at this point will be 0, right? And these are the critical points that we're talking about. So don't mind my drawing, it's very poor, but I think you get the point. So we expect the derivatives at those turning points to be 0, right? So this is why this must be true. And we need to solve for the values of x that make this particular equation to be true. Now let's do that. So dy dx is derivative of this. So we know that what our y is this x cubed over 3 minus x squared over 2 minus 2x plus 5. So all we need to do is to find the derivative of this, which is 3. So we can take the constant out and just take the derivative of x cubed, which is 3x squared minus 1 over 2, 2x, then minus 2. Okay, so when you simplify, this gives x squared minus x minus 2. So all we need to now solve to get the critical points is this equal to 0. And if you know a little bit of quadratic expression, you know quickly that we can factorize the left-hand side to be x minus 2, x plus 1, okay, equal to 0. Now that you have this, so the critical points would be x minus 2 equal to 0, x plus 1 equal to 0, and that would give us x equal to 2, x equal to minus 1. So these are the critical points. So critical points are x equal to minus 1 and 2. Now, when you have this, the next step is to classify the critical points. Okay, so let's quickly classify them. Classify them into being maximum, minimum, or saddle points, okay? Now, so there are two ways to do this. The first step, which is the first method, which is what I'm going to explain now, which would be second derivative test. So the next thing we use second derivative test. So what you do is you take the second derivative of the first of the function, which means you have to take the derivative of the first function, of the first derivative. So the first derivative was this, right? So in taking the second derivative, we have to take the derivative of this function. And this quickly gives us 2x minus 1. So this is the second derivative. Now, what do we do here? We try to evaluate the second derivative at the critical point. At x equal to minus 1, y prime prime would be what? 2 minus 1 minus 1, and this gives us minus 3. And at x equal to 2, what is the value of the second derivative? That gives us 2 bracket 2 minus 1, which gives us 3. Now, how do we classify these points? So in case you don't know the theory behind this is how we look at it. When we have a negative value at the second derivative test for the critical point, when we have negative value, when this is negative, we call it what? Concave down. This implies the function is concave down. So down representing the negative, right? So we call it concave down, which means this. So this tells us that what we have a maximum at this point at x equal to minus 1. Now, when you have positive, it means this is what? Concave up. So that's how to simply recognize it, concave up, right? And then you know that what? You have a minimum at this point. Okay, so we can easily say that at x equal to minus 1, f achieves maximum. So we can quickly conclude this. And at x equal to 2, f achieves minimum. And we could find those values. So what is y? What is the function at x equal to minus 1, which is, remember the function is x cubed. So minus 1 cube over 3 minus 2, minus 1 square over 2 minus 2 times minus 1. I think if that's the case, yes. So plus 5, right? Plus 5. So when we evaluate this, we have minus 1 over 3 minus 1 over 2 plus 2 plus 5. So that will give us 7 minus, this is 6. This is, I think, 7 minus 5. Yeah, 7 minus 5 over 6. So which is basically 42 minus 5, which is, what does that give us? This is 30, I think 37 over 6. So this is what we have as the maximum of this particular function. Okay, what about the minimum? So the minimum value, so when x is 2, f will be what? 2 raised to the power 3 over 3 minus 2 square over 2 minus 2 times 2 plus 5. So this gives us 8 over 3 minus 4 divided by 2, that is 2, minus 4 plus 5. So this is just 8 over 3 minus 6 plus 5, that's minus 1. So that means we have 8 minus 3, 5 over 3, right? So this is approximately 1.67. And what about the first one? 36 divided by 6, that is approximately 6.1, okay? All right, so you can see this will be the maximum and this would be the minimum. So for maximum, we could quickly write out the coordinates. The coordinates of that is, for maximum, we have minus 1, 37 over 6. For minimum, we have 2, 5 over 3. Okay, and that solves the problem. All right, now this is using second derivative test. What if we decide to use the first derivative test to determine this? And that is the second method. So second method, second way. Now, the first step is still, step 1 is still the same. So step 1 is, we still find the derivative with respect to x equated to 0, and you obtain the critical points x equal to minus 1 and x equal to 2. Now, the second step is this, step 2. We make a table, right, to understand what happens to this function at the first derivative, right? So this is the first derivative, and this is the values of x. Now, you put your critical points at this junction. So we have x equal to minus 1 here. So arrange it in terms of how the ordering is when you look at it from the real line perspective. So minus 1 comes before 2. So we put minus 1 here and 2 here. We know that what the derivative at this point, that is how we got them in the first place. The derivative at this point are 0. Okay, we know there's the first derivative at x equal to minus 1 and 2 are 0. Now we pick some points just close to -1. A convenient number to use here will be -2. Now we'll pick a point between -1 and 2. A convenient number will be 0, and then we'll pick a point after 2, which is 3. Now we're trying to understand the derivative at this point. Now, why are we doing this? Because what information is encoded in the derivative of a function? The information there is where it helps us to find, so y prime or f prime helps us to know if a function is increasing or decreasing. Or decreasing at a point. Okay. So in fact, on an interval, basically, right, it helps us to know if a function is increasing or decreasing in an interval. Okay. So we are looking at all the points closer to -1 from the left-hand side, right? And we just picked a point here to illustrate what happens to the function at those points. So now, of course, if f prime is positive at a point, it means it is increasing. So if f prime of x is greater than 0, it implies f is increasing. And if f prime is less than 0, it implies f is what? Decreasing. Okay, so now let's look at this. So f prime at -2, that will just give us what? Remember, I think f prime of x, we got it before, is x squared minus x minus 2, right? That's what we got before, right? Okay, so now f prime at -2, that will be -2 squared minus -2 minus 2. So that would give us 4 plus 2 minus 2, which is 6 minus 2, which is 4. Okay, so it is 4, right? It means at this interval, f prime of x should be what? Increasing, because it is positive. Okay, so we make an arrow up to tell us that what the function is increasing in that interval. Now notice that what this is not peculiar to only -2. If I had chosen -5, -7, the same thing will still be true. So you can just check it out. Now let's check f prime at 0, which is the next one. F prime at 0 will be 0 squared minus 0 minus 2. So that is -2. It is negative, so it means it will be decreasing on this interval. Okay, the interval between -1 and 2, the function will be decreasing. And finally, f prime at 3, that will be 3 squared minus 3 minus 2. So that is 9 minus 5, which is 4. It is also greater than 0. So which means it will be increasing again beyond 2. So the function from this interval 2 and above would be increasing. Now, what does this tell us? Where you see the arrow is going up and then moving down, it means there is a maximum here. And when it is moving down, then back up, that means there's a minimum here. So we can conclude that what? At x equal to -1, f is maximum. So f achieves maximum, and at x equal to 2, f is minimum. So basically, once you get this, you just need to find the values of f. So you go through the method again to find f, and f would be, was it 37/6? So we get 37/6, which will give us the maximum. And again, you try to find the value of y, right? When x is equal to 2, and that gave us 5/3, okay? At minimum. And that completes the problem as well. So this is how to find the minimum maximum values of a function. Now, sometimes you might have saddle points. Some of you might be asking, so what happens, what happens when f is increasing here and then also increasing here? Okay, this is just an addition to this problem. So let's say we have increasing here and also increasing here. This tells us that what? This point would be a saddle point. Or when the function is decreasing here and then decreasing here. So this tells us that what we have is saddle point, not a minimum or maximum, right? So this is just an addition to the information I've already given you about the minimum and maximum values of a function. All right, if you like this video, make sure you like and then subscribe to the channel to help its growth. And I'll see you in the next video.